Hi everyone, it's Michael. So I have a terrific problem for you all today. This problem was part of the ELMO math contest in 2016. So as I mentioned before, that's a math contest that's part of the Math Olympiad Summer Program in the US. So if you'd like to try to solve it, feel free to pause the video. All right, so I'm going to go over the solution. So we have a triangle ABC, and we draw the two tangents to the circumcircle, and they meet at point D. Then we let B prime be the reflection of B across the side AC, and C prime is the reflection of C across AB. And we let O be the circumcenter of triangle DB prime C prime, and we want to show that AO is perpendicular to BC. So this problem was very tricky for me. I feel like it's much harder than the diagram makes it look like. So I'm going to start out first by pointing out some things that are easier to see. So if C prime is a reflection of C over AB, then it's clear that triangle ABC prime has to be congruent to triangle ABC, and the same is true with triangle AB prime C. So I'm going to draw in those lines for those triangles. All right, so where do we go from here? So since all three of those triangles are congruent, it's clear from that that BC prime is equal to B prime C, because they're both equal to the side BC, and also BD is equal to DC. So that makes us wonder, could it be that triangle C prime BD and B prime CD are congruent? They kind of look congruent in the figure, and it turns out they are. So I'm going to do an angle chase to show that to show that angle B prime CD is the same as angle C prime BD. And if that's true, that would show those two triangles are congruent. All right. So first I'm going to calculate angle DCB prime. It's equal to the sum of these two angles, so B prime CA and BCA, plus angle BCD. And those two angles in the parentheses are both equal to angle ACB by symmetry, since B prime is the reflection of B over AC. Okay, so this angle DCB prime is equal to twice angle ACB plus angle BAC. And so I should mention I am assuming something about the configuration here. I'm assuming that basically DB prime intersects the two of the sides of the triangle, whereas C prime D lies outside of the triangle. But the same idea would be true in a different configuration. We could still use a similar idea to show that angle DCB prime is equal to angle DBC, or DC prime B is equal to angle DBC prime. Okay, so I've calculated this angle here. Now I'm going to calculate this angle here. So angle DBC prime, it's 360 minus these three angles. And these two angles right here are both equal to angle ABC by symmetry. And this angle here, angle DBC, that's equal to angle BAC, since DB is tangent to the circumcircle. Okay, so we have 360 minus 2 angle ABC minus angle BAC. And 360, we can rewrite that as 2 times 180, which is 2 times the sum of the three angles of triangle ABC. So I'm going to do that. So that's 2 times angle ABC plus angle ACB plus angle BAC minus these angles. And the result of this is the same expression that we got for angle DCB prime. So from there, it's fairly easy to conclude that these two triangles have to be congruent. So I'm going to write this out. But we just showed through a calculation that angle DCB prime is equal to angle DBC prime. I wonder if there's a way to show this without a calculation, but that's how I did it. And then clearly DB is equal to DC because they're both tangent to the circle. And C prime B is equal to BC, which is equal to CB prime. And so from there, by side angle side, we have to have those two triangles are congruent. All right. So once we know that these two triangles are congruent, that means a rotation about D takes one triangle to the other triangle. And if that is the case, a rotation is a kind of spiral similarity. And so there's something I did here that I've seen in other problems before. And that is, we can try, whenever you have a spiral similarity like this, triangle with these two triangles, if you connect the two sides that are not attached to point D. So I'm going to let BC prime intersect B prime C at a point. And I didn't know this would solve the problem, but I just tried it out and it ended up working. Okay, so I let E be the intersection of BC prime and B prime C. And then there's a theorem that says that DEB prime C has to be cyclic. And that might come in handy because we know that O is the circumcenter of DB prime C prime. So if we can find one other point on the circumcircle, maybe that would help solve the problem. So I'm going to prove that E is actually on the circumcircle. It's just an angle chase. So we have angle, actually before I do that, I'm going to prove a different quadrilateral is also cyclic. So I'm going to show DBCE is cyclic. That's just an angle chase. So angle DBE, it's 180 minus DBC prime. And that's the same as 180 minus DCB prime, since those two triangles are congruent. And that's angle DCE. So B, C, E, and D are cyclic. And not only that, it's not too hard to show that the circumcenter of triangle ABC also has to lie on that circle. So I'm going to draw the circumcenter F of triangle ABC. But FBD and FCD are both right angles. They're both 90 degrees. And so FBDC has to be cyclic. And so all 5 of those points have to lie on a circle. So I'm going to draw in that circle. But this is something I'd recognized even before I solved the problem. That if you have a spiral similarity of two triangles, so in this case it's just a rotation, but any spiral similarity, if you take the two sides not attached to point D and you extend them, it forms a cyclic quadrilateral here. And then not only that, it forms another cyclic quadrilateral, like I mentioned. Just as DECB is cyclic, we also have DEB prime C prime is cyclic. Okay. So this is the angle chase that proves it out. It's kind of a well-known fact, but I haven't done a video on spiral similarities yet. So we have angle B prime EC prime is equal to angle CEB, which is equal to angle CDB. And if you look at angle CDB, I claim it has to be the same as B prime DC prime. And that's because if you start with angle CDB and you take away this angle, CDB prime, but you add in BDC prime, it has to stay the same. But those two angles are the same because they're from congruent triangles. And so if you go through this angle calculation, we have angle B prime EC prime is the same as angle B prime DC prime. And so we also have B prime EDC prime is cyclic. Okay, so I'm going to draw that. And so how does that help us here? Well, so first of all, I'm going to note that if you look at points A, F, and E, they kind of look collinear from the diagram, and it turns out they are. So that's going to be the next step in my solution. So note that, so F is the midpoint of arc BC of this circle. And so FB is equal to FC. That's true because FB and FC are both radii of the circle through A, B, and C. And so that means that EF has to bisect angle BEC. So I'm going to write that out. So since FB is equal to FC, EF is the angle bisector of BEC. Okay. And now I'm going to show that angle now I'm going to show that EA is also the angle bisector. So it turns out that C prime ACE is also cyclic. And that would help show that because we know that C prime A is equal to AC. So that would mean that EA is also the angle bisector of BEC. So I'm going to show that this quadrilateral is cyclic, and it's a fairly straightforward angle chase. So we have angle AC prime E is equal to angle AC prime B, which by symmetry is equal to ACB, and by symmetry that's equal to angle ACB prime. So AC prime EC is a cyclic quadrilateral. So we have lots of cyclic quadrilaterals here. But in particular, we know that AC prime is equal to AC. So EA has to be the angle bisector of C prime EC. And from there, we have that EF and A are collinear because they all lie on the angle bisector of this angle BEC. All right, so EF and A are collinear. So what I'm going to do is I'm going to draw the line through those 3 points, and I'm going to see where it intersects the big circle. Okay, so I'm going to let it intersect the big circle at a point G. And now I'm going to note something. So we know that FD is a diameter of this circle. Where have I let FD is a diameter of the circle FCEDB. And so angle DEF has to be 90 degrees. And if angle DEF is 90 degrees, then that means that angle DEG is also 90 degrees. So DG is the diameter of the big circle. And so it has to pass through O, which is the circumcenter. Okay? All right. So D, O, and G are collinear, and DG is a diameter. Where do we go from here? So ultimately, we wanted to show that AO is perpendicular to BC. We know that it's easy to see that DF is perpendicular to BC, and O is the midpoint of GD because it's the center of the circle. So if we could show that A is the midpoint of GF, that would solve the problem. And here's where I start using more facts about spiral similarities. So I'm going to try to use both facts about spiral similarities and the gliding principle, which I mentioned before in my channel, to try to solve this problem. So we have a right triangle DB prime G, and we also have a right triangle DCF. And it's not hard to show those are similar, which I'm going to do later. But DB prime G and DCF, there's a spiral similarity that takes one to the other. So if we use the gliding principle, and we let okay, so here I prove that those two triangles are similar. So angle DCF is 90 degrees because DF is a diameter, and angle DB prime G is also 90 degrees because DG is a diameter. Okay, and then it's not hard to show that angle FDC has to equal angle GD or B prime DG. So I do that calculation here. So FDC, it's obviously half of angle BDC, and we said before that angle BDC is the same as angle C prime DB prime. So from there, it's easy to see that angle FDC has to equal angle B prime DG, and so those two triangles are similar. Okay, so I'm going to make some more room here. So thanks for waiting for this. Okay, so triangle DCF is similar to triangle DBG prime. So by the gliding principle, that means if we take the midpoints of CB prime and the midpoint of FG, those 2 points, if you connect them along with D, should form a triangle similar to both of those. So I'm going to label the midpoint of CB prime. I'm going to label it H. And I'm going to label the midpoint of BCJ. And you'll see why that comes in handy later. But basically, you want to show that triangle AHD is similar to both triangles DCF and DB prime G. And so then it would follow from that in the gliding principle that A is the midpoint of FG. All right. So how do we show that triangle AHD is similar to both of these triangles? Well, what I'm going to do is I'm going to show actually that there's a spiral similarity that takes triangle BJD to triangle AHD. And that would help get us there. And for those of you that know about spiral similarities, that's actually the same as showing that triangle DBA is similar to triangle DJH using properties of spiral similarities. So I haven't done a video on my channel on that yet, but hopefully I will soon. Okay, so I'm just going to draw on another line, and I'm going to let K be the intersection of these two segments. It's not too hard to show. So in order to show that, I ultimately want to show that triangle ABD is similar to triangle DJH. And as a step in it, I'm going to use the fact that triangle DBJ is similar to triangle BAK. So that's not hard to show. So I'm going to do an angle chase here. We have angle DBJ is equal to angle DBC, which is equal to angle BAC. That's because DB is tangent to the circle. And angle BAC is equal to angle BAK. So since DBJ is equal to angle BAK, and they're both right triangles, we have triangle DBJ is similar to triangle BAK. All right. So now that is the first step. So now I'm going to try to show that triangle DJH is similar to triangle DBA. So I'm going to show that the ratios of DJ and DH and JH is the same as the ratio between DB and BA, and also that the angle between them is equal. All right. So we have JH over AB. That's the ratio of two sides in the triangles DJH and DBA. So JH over AB. Well, JH is a mid-segment in triangle BB prime C because J and H are both midpoints of those two sides. So JH is BB prime over 2. So JH over AB is BB prime over 2AB. And BB prime over 2 is BK, is just BK by symmetry. So this is BK over AB. And then using this similar triangle right here, that's the same as JD over DB. So we have that JH over AB is equal to JD over DB. So that means that the ratio of corresponding sides in these two triangles is the same, DJH and DBA. Now we just have to show that angle DJH is equal to angle DBA. So I'm going to do that right now. That's just an angle chase. That's not too difficult. So we have angle HJD. That's 9. So angle DJC is obviously 90. So that's angle 90 plus angle HJC. But HJ is parallel to BB prime because, like I said, it's a mid-segment. So angle HJC. Actually, I thought of this a little differently. So angle HJC, it's clear that by symmetry that HJ is perpendicular to AC. So angle HJC is 90 minus angle JCA. And so this angle JCA is BCA. So this is 180 minus angle BCA. And because BD is tangent to the circle, that has to be the same as angle ABD, because 180 minus angle BCA, that would be the same as an angle that intercepts side AB, but on the other side of the circle. And so since BD is tangent to the circle, let's say G was some point on this arc right here. Angle AGB is 180 minus BCA. So, but AGB would be the same as angle ABD because BD is tangent to the circle. Okay, so we showed that angle HJD is equal to angle ABD, and so we did the last part of what we need to show those two triangles are similar. So we have a spiral similarity takes triangle DJH to triangle DBA. And so for those of you that know about spiral similarities, that means it also has to take triangle DJB to triangle DHA. So, I'm going to write this out. So basically we have that triangle AHD then has to be similar to triangle BJD. And triangle BJD it's very easy to show that that's similar to triangle DCF because they're both right triangles and they both share a common angle. And triangle DCF, we mentioned before that that's similar to this triangle DB prime G. I mentioned that right here. So triangle AHD, it's similar to both of these two triangles, DB prime G and DCF. And H is the midpoint of B prime C. So by the gliding principle, or the converse of the gliding principle, A would have to be the midpoint of GF. Because if you have two similar triangles, so we have the two similar triangles DCF and DB prime G, the midpoints of corresponding vertices have to form another similar triangle. So since we know triangle AHD is similar, A is the midpoint of GF, and that gets us where we want because we know that O is also the midpoint of GD, and so that means that AO has to be parallel to DF, okay? Because if O is the midpoint of GD and A is the midpoint of GF, AO is parallel to FD, and it's clear that FD is perpendicular to BC because FD is a diameter of the circle. And so AO also has to be perpendicular to BC. So I found this to be an incredibly difficult problem given that the initial diagram doesn't look that complicated. So I feel like on the Art of Problem Solving forum, I only saw one solution that really I thought was fairly simple and not super involved. But I feel like this teaches you a lot about spiral similarities. So I hope if you didn't already know about them, you learned something with this. So if you liked the video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.